respect to P, we'll call L the expected description length per symbol of X is equal to, so this is by definition, that's L, and that's equal to summation P log P P log 1 over Q. Let me put a log here. All right. So this is the L of X, and this is the P of X. So that's the expected thing with respect to the ideal code word lengths for Q. But look, this sum we multiply and divide by P to get it in a relative entropy setting. And then we notice that the first term is dpq. And the second term is h of p. If we knew P were true and we designed a L, the description length for that P, we would achieve the entropy H of P as the description length. But since we thought it was Q, it costs us an extra dpq bits per symbol. So that's the cost of being wrong. Notice that came up in gambling. If you gamble as if Q is true, and in fact P is true, your money may go, has an exponential growth rate, but the decrement in your growth rate beyond, below the maximum is dpq, how far off you are in your assessment of the underlying distribution. So for the wrong code, expected value of P of L sub, I won't define this, L sub Q of X, ideal code word there, code length is there, is H of P plus dpq. So that's the cost of being wrong. By the way, let me take a quick digression here. Here's the true distribution, P. Here's Q. And the entropy, H of P, is what it should cost you, but you thought it was Q, so it costs you H of P plus dpq. Now, somebody in office hours asked, what if you have a couple of distributions, P1 and P2, and I don't know which is true? Well, then it turns out you want to choose the Q that's an equal distance from P1 and P2. Because that equalizes the cost. If this is true, you pay that cost. If this is true, you pay that cost. So you want to minimize the maximum distance, which is you want to find the Q sphere that has center Q and has minimum dpq radius that includes the sources that you're trying to be universal with respect to. So the radius of the minimum information ball that contains all the distributions that you hope to be good with respect to will cause you to pay just an additional deep, this radius, dp star q, above the ideal compression rates associated with each of the sources. In this case, Q will lie on the line between P1 and P2, but if there's a P3 and so on, it will be the center of, it's a little more complicated, but you can get it by an iterative procedure. This could be text, this could be a file, this could be music, this could be IID horse race results, and you'd want a compression scheme that would take any of those sources and compress them to their ideal entropy limit. And you can do that if you're willing to pay this extra cost of the radius of dpq. Nice, huh? The niceness doesn't end there, but what I'll be saying about it will. Using the min-max theorem, you can show that this radius is channel capacity for a channel that has rows in the transition matrix given by P1, P2, and P3, showing a beautiful duality between data compression, universal data compression, and data transmission, which is the number of distinguishable bits you can get through a channel that has these noise outcomes as a function of what symbol you send. 1, you get this distribution. 2, you get that. So, nice, huh? That, of course, will come up at the appropriate time next quarter. Okay, so much for that digression. Now, any questions on this? Because I'm going to talk about arithmetic coding. All right. Yeah. H of Q? Well, Q isn't the true distribution. So Q is a distribution, the way I've drawn it over there, which is sort of uniformly close to all of the hypothesized distributions that might be in effect. So which distribution, and then we code as if Q is true. Then if P1 is true, we pay, and we get data compression H of P1 plus D P1Q. So we pay a penalty for the universality. In other words, we sort of have this sludgy Q, and that's sort of like a mixture of all the sources. But what mixture? That comes from the geometry of dpq. The Q should be the center of the lowest radius dpq sphere, if you wish, that contains all the P's. Does that answer? Oh, which one? Yeah. Oh, yes.
So if I did a wrong course and then I looked at the results,
Yeah.
would there be any way for me to know that I have a wrong course?
Oh, yeah. If you only get one outcome, X, you can't estimate P of X. You just see an individual outcome, X equals little x. But if you repeat this IID many times, you can find the empirical distribution p hat of x. And p hat of x will converge to p, the true distribution, and not to q, the distribution that you've been using. So yes, in repeated plays of this game, you can say, you know what, I've been designing a code for the wrong distribution, and I should change my code word length accordingly. Right. So, let's look at arithmetic coding. Then after that, we'll look at Huffman coding, the best you can do. But arithmetic coding is what is done most often in practice, partly because you get to assume something about the source that may be wrong, but code and decode accordingly. And you can do it on the fly, and it has lots of good properties. So, I'm going to state a fact first that seems unrelated to data compression. Let x have cumulative distribution f of x. And of course this is the probability that the random variable x is less than or equal to little x. So f of x looks like this. Here's x. It's monotonic, increasing. And suppose it has no jumps. That means it has no atoms. There's no outcome that has strictly positive probability. It has a probability density, or actually it could have a singular part, like the Cantor ternary function. So, the theorem let u equal f of x. Notice we were self-referential before. We said, oh, let x have probability mass function p of x. And now let's see how the distribution of p of x. Well, here we look at the integral. We say, let x have the cumulative distribution f of x. And now let's evaluate f on x that's drawn according to f of x. What can we say about the distribution of f of x? And the theorem is if f has no atoms, no jumps, then u is uniform over this interval 0, 1. That is, it has this distribution. This is sort of f of u. Or, if you wish, it has this distribution, f of u. Now, that's nice, and it's very useful. It comes up in lots of